This is another topic, and this is very, very important because the electrodynamics is based on the Maxwell's equation. Here, the topic is Maxwell's equation. Before Maxwell's equations, the scientist developed the following laws for electrodynamics. The first one is divergence of E, which is equal to rho divided by epsilon naught, and we know that this is the Gauss's law. The second one is divergence of B, which is equal to 0. It has no name because there is no magnetic monopole, so always the divergence of the magnetic field will be equal to 0, so no name here. And third one is del cross E, which is equal to minus partial P divided by partial T, and this is known as Faraday's law. And the last one, this is del cross B, which is equal to mu naught J, and this is known as Ampere's law. These are the equation before Maxwell's. One is the Gauss's law, divergence of electric field, which is equal to rho divided by epsilon naught. Divergence of this is equal to 0. Curl of E, which is equal to minus partial B divided by partial T. This is a Faraday law. And divergence of B, which is equal to mu naught J. This is Ampere's law. These equations were not in a compact form as presented above. These equations were not in the compact form that I have write down like this before Maxwell's. These equations represented the state of electromagnetic theory in the mid of 19th century. And there is some inconsistency. There is some inconsistency in these equations before Maxwell's. As from our previous knowledge, we can say that the divergence of curl, will always be equal to 0. This has been confirmed that the divergence of any curl must be equal to 0. Now, if we apply this concept to equation 3, if we use this concept and apply the divergence at both sides of equation 3, then what we will have? Applying this concept to equation 3. What we have, divergence of curl of E. We can also apply this side, divergence partial B divided by partial T. If I write down like this, and if I take this divergence out inside this, then I have the form as as we know that the divergence of curl is equal to 0, this left hand side is equal to 0, and the divergence of this magnetic field, we know from equation 2, this will always be equal to 0. So this equation is satisfied. The left hand side is equal to 0 and the right side is equal to 0. So this equation is satisfied by using this concept. Now what will happen if we apply this concept to equation number 4? Take the divergence of equation 4. So divergence of curl, which is equal to mu naught divergence of this. It's clear that this is equal to 0. If J is not constant, this divergence may not be equal to 0. For the constant J, it is clear. If we have J as constant, then it means that this is equal to 0 and this is equal to 0. But always J as not remains constant. Then what will happen? This, if this is not constant, it means that we have divergence of J. And the same value we have, the left hand side and the right hand side is not equal. So there is some problem in this equation. How to fix this equation which has the left hand side and the right hand side both are equal? If the current actually this is the current density, current per unit area, if the current is constant, then for steady state, the above equation is valid. But if current is not constant, then we have to face some problem. If the current is not constant, we have to face some problem, and this equation number 4, then how to fix and how to correct this equation number 4. This was the main point that Maxwell fixed this equation, and this equation is not like this, and they have done some modification. Let's see this in the next lecture.